Hi everyone, how are you? I hope that all of my students are doing good in their lives. So let's start with the chapter 2, which is about regular languages and the regular expressions. So here on the screen, so this is session 2 for us. So on the screen, you can see that now we are going we are moving towards regular languages and regular expressions. And before that, we studied some introductory material in chapter 1. Uh, we had seen mathematical induction and recursive definitions in chapter 1 that I hope that you have read that material from the textbook. And in our chapter 1, there was a principle of mathematical induction, then strong principle of mathematical induction, and there are some recursive definitions of different functions with respect to some domain, and recursive definition of sets, mathematical sets, and then structural inductions. So this is something you have seen in chapter 1 of Introduction to Languages and Theory of Computation uh, by John C. Martin, the book which is we are following in this course. So now let's start with the chapter 2. So in chapter 2, we have to focus on now the detailed understanding of regular languages and regular expressions. So now we will focus that what is a regular language. So the definition of the regular language is in front of you in these lines. So first I'm going to read this sentence and then I will explain these things to you. So assume that we have a set R of regular languages over sigma. And now I hope that you understand, you have the understanding of sigma. So sigma is what? Sigma is an alphabet set. So, so suppose we have a set R of regular languages over sigma, and the corresponding regular expression uh, can be defined for these regular languages or for this regular language are as follows. So if I will talk that this is a regular language, then you must have to put in your minds that we can build a regular expression for that regular language. So, and now we are supposing that R is a regular language, then there must be some regular expression, but that regular expression must have these things in it. Number one, phi is an element of a R. So phi, and what is phi? We have seen that it is a kind of an empty set. So phi is an element of R, and the if so if there is a regular language, then we have the regular expression for that regular language, and the first condition that must have met is phi should be an element of that regular language R, and the regular expression for that phi would be simply phi. And if null, and you are seeing some curly brackets over null, if it is an element of a regular language, then the regular expression is simply null without curly braces are like that. Number 3, if we have some element, some alphabet A, which is belonging to alphabet set, and we can write that element within the curly brackets or braces is an, if this is an element of R, so now in place of this A, you can assume that you are representing an alphabet, and it could be any alphabet, A, B, C, X, Y, Z, whatever. So that's why it is written here as for each A belongs to sigma. If A and curly braces is an element of R, then we can write the regular expression for that element of R as simply A without any curly braces. Number 4. So up to that point, we have seen phi, we have seen null, we have seen any element for that regular language. And now number 4, if L1 and L2 are any elements of R, which is a regular language, if this L1 and L2 are any element of the alphabet set of this regular language, then their regular corresponding regular expressions would be R1 for L1, R2 for L2, be their corresponding regular expressions. And if it is the situation, then we have 3 more conditions that we have to check for the regular language. So the first condition is that L1, you have to take union, L1 union L2, with L1 and L2 are the elements of that regular language, or you can say the elements of that uh, uh, alphabet set. So L, you have to take the union, and so this is some kind of representation of an elements, but if we want to represent it into the form of regular expression, then RE is equal to R1 plus R2. And what is this plus? Plus is a symbol that you can use to represent this union. So this R1 plus R2 means R1 is the regular expression for L1, R2 is the regular expression for L2, and this plus is to represent this union. So if you are building regular expressions, then you cannot use this expression, or you cannot use this mathematical symbol U, which normally we use for sets, but you can use the plus symbol in place of this union in a regular expression. Similarly, for this is the union case, this is the concatenation case, and this is the clean star case. Okay, in concatenation, if L1 concatenated with L2 belongs to regular language R, then its regular expression would be simply R1 and R2, and then you have to put the parenthesis. So you have to put the parenthesis, R without parenthesis. C is L1 only, and you can take L2. So here, for understanding, we are taking L1. So L1, and then we have a clean star over it. And what is the meaning of star? It means that all possible combinations of alphabets, elements, alphabets simply, including null. That is something that we have seen in our first lecture. So uh, you can visit the slides of your first lecture, and then you can see these things again. So L1, and you have to, if we have a clean star over it, then, and if it belongs to a regular language R, then its regular expression is equal to R1 star. You can also put parentheses if you want, but as I said, sometime you can represent. यार ना शोर मचाओ, बीच में आपकी चीजें आती, मेरी सारी मेहनत जाया हो जाती है। क्यों आते हो फिर इधर? वो उधर खिड़की में पड़ी है कोने में। Okay, so it is up to you. You can place parentheses here, or you can represent regular expressions without parentheses. But when you will practice this making of regular expressions, then you will see in future that sometime parentheses are compulsory to represent precedence. And this topic will come, we will see these things. So after reading all these conditions, now we can say that uh, hence languages that can be obtained using 1 to 4 are regular languages. So we have seen one, two, three, four, and so on. So now I can say that the languages that I will get by using these four conditions from 1 to 4, and the strings that I will produce for that language uh, using this 1, 2, 3, and 4 for some particular language, then if all the conditions would be met from 1 to 4, then I can say that that language is a regular languages. Or in a short version, I can say the languages that uh, I can produce using 1 to 4, those languages would be called regular languages. Okay, so now, so this is something theoretical stuff. If some of the understanding of this text you have not get it accurately, then don't worry, you will see these things uh, in next examples and all the concepts will be clear. This is a little bit drawback of this online classes. If that would be physical, then you will understand many things by the body language of a teacher. So anyhow, so leave it and now move on. By the way, leave this January 2010. So this is the diary which I used. It's an old one. Otherwise, the text is not the old one. It is something new, according to the third edition of John C. Matter. So now I am going to explain that what are the simplified rules uh, to to build a regular expression for a particular language, and that language would be regular. We know that because regular expression is always for those languages which are regular languages. So, what are those simplified rules? Number one, what you have to do, you have to discard the curly braces if it is present in the definition of that language. Then you have to discard those curly braces, and then you have to replace these curly braces with the parentheses. And then number two, you have to replace this symbol U with plus, which is for union. For example, this is the column for languages and this is the column for their respective regular expressions. So if language is like this, represented with curly brackets and have a symbol null here, then the regular expression is simply null with parentheses or without parentheses. And then if this is the language, zero, language of zero, then you can simply represent it with 0 with parentheses or without parentheses. Again, if we have a language like 001 and with curly braces, or I can also represent it with 0 curly braces concatenated with 0 and concatenated with 1, all elements in separate curly braces. So this is very much similar to this one. So you can represent this language in this form if you want to build a regular expression of this language as 001. So you can also write parentheses uh, um, around this 001. Similarly, for 0 and comma 1 and then curly braces. Here, comma means whenever you will see comma in the definition of a language, uh, in the mathematical definition, this is mathematical definition. It's not theoretical statement. So sometime I will give you the languages in theoretical statements, like in sentences, and then first you have to convert those theoretical sentences into mathematical definition, and then you have to convert it into regular expression. So but here we have the languages in mathematical form. So 0 comma 1, whenever there is a comma between the alphabets or the strings of a language, then it means that here comma means union. Keep this thing in your mind. So I can write it as 0 and then union and 1. So this is again the same thing as this one. And if this is a union, so I know that I can replace this symbol U with plus, and then 0 without braces and 1 without braces. So it becomes 0 plus 1. Similarly, 1 comma null braces, 001 braces. So this is the definition of the language. And how can we convert it into regular expression? So this comma is a union. So 1 plus null, you can see it here. So then we can put parentheses and then 001. So we can remove these curly braces and then we will have 001 only. So now I will explain something later on. Uh, there is a concept here. How this one? So leave it. I will explain these things. So this is the regular expression for this language. Now next is 110 and clean star and then curly braces 0 comma 1. Here comma means union, and this is the clean star that we have seen in the definition of this one. So now I can represent it with 110 with braces, with parentheses, and then I can put star over it. And here this one is simple. So 0 plus 1. So 0 plus 1 is okay, but I have to put parentheses for clarity. So this is the regular expression. And similarly, 0 comma 10 clean star and then parentheses and then 1 star union 0 comma null. So okay, this one is simple. Comma is a union, so 0 plus 10 here and then star over it. So just parentheses and star, and then this is 1 unit again. So this 1 put some parentheses and star like this one, and this is the u which I will can replace it with plus, and then this is 001 comma is again union, so I can replace it with plus also. So 001 plus null, and then you can put parentheses. So this is the representation. This is the regular expression. So now I said that these are the mathematical definitions of a language. I can represent these mathematical definition of a language in the form of sentence in a theoretical statement. For example, here 1 star 10 is a this is a mistake. So this is a regular expression for strings. If this is a regular expression, so this regular expression is a regular expression for a language that consists of substring 10 preceded by any number of ones. So here 1 star means I can produce null, I can produce 1, then I can produce 1 1, I can produce triple 1, and so on. For example, this is not the time, but sometime a teacher feel that it is better to represent something on the board. So for example, here 1 star and then 10. So this is a regular expression. And what it is representing, it is what this one star is representing. So one star, if I open it, then it would be, the elements would be, first I can produce null, then I can produce, if I repeat it with uh, one time with power 1, then it would be only 1. If I repeat it 2 times, then 1 would be produced. If I repeat it with 3 times, then triple 1 could be produced, and so on. So this is the explanation of one star. And 10 is what? 10 is a complete string which cannot be changed. It is the compulsory part of a string that can be produced from this whole regular expression. So I can produce null from here and 10. So 10, only 10 is a valid string of this regular expression. Similarly, 1 from here, after repeating it once, and then 1 0 from this part, because this is the compulsory part of every string. Here compulsory part 10, here compulsory part, and this one is coming from here. So this is again a valid string of this regular expression. Similarly, sorry, similarly, I can write triple one. Triple one, for example, triple one is here, valid part. Triple one, and then this 10. This 10 is from here, and this triple one is from this part. So this is also a valid string of this regular expression. So now you will understand. Now come to these slides. So 1 star 10 is a regular expression for strings that consist of substring 10 preceded by. Preceded means something which occurs first from something. So 10 preceded by any number of ones, including nulls. So null can precede this 10, 1 can precede this 10, double 1 can precede this 10, triple 1 can precede this 10. And in this way, you can produce different strings from these regular expressions. Okay, similarly, if there is something written in this form, L square, then it means that LL, it is a concatenation of L and an L. And if something is represented with R square, then it means it is RR. If something is represented with R plus, then plus you already know from your lecture 1. Star means all possible strings, including null. And plus means all possible strings without null. So R plus can be equal to a regular expression on the right hand side, and it is written here as R star into simply R and then parenthesis. Maybe some of you would not understand, but this is here, but here left hand side is perfectly equal to the right hand side, and you can see this thing here. For example, R plus, I can maybe how can I resize the screen into a bigger one? I am just searching the option. If it is available, then I will make. Okay, maybe I can. No. I can stop sharing and then maybe you will see the video only. Yes. Now look over here. R plus is equal to R star into R. This is something written there. So how it is equal? For example, what is R star? R star is, I can write it null, then 1R, double R, triple R, and so on. This is the full form of this R star, and this is single R. So now you can multiply all these elements with this one. So take this one, null, multiply with this R, what you will get? R. When a null, this is an element, when null element is multiplied with this R, for example, null and R, what would be the result? R. So after multiplying this null with this R, what you will get? R. After multiplying this R with this R, what you will get? Double R. After multiplying this double R with this R, what you will get? Triple R. And so on. Again, the same language, but without null. And what is this one? This is, I can say that this is equal to R plus all possible combination of R, which is this one, without null, and we don't have a null here. So that's why this R plus is equal to this one. This left hand side is equal to this one. Okay, now we can move back to our notes. Okay. So now you can see on the screen that this R plus is equal to R star into R. Now move on. Precedence. Now we are studying regular languages and regular expression, but there is another subtopic that is called precedence. Up to now, we have seen clean star. We have also seen the concept of concatenation, like this one, L1 and L1. This is concatenation. Or this one may be here. You have seen L1, L2 belongs to R, and this is also a concatenation. So there we have seen the concept of concatenation, and then we have seen the concept of union plus. And we have seen these three different operators, you can say. And then there would be some precedence mechanism. So the first precedence is the precedence of clean star, then the second precedence of this concatenation operator, and third is the precedence of this union symbol, plus or u or whatever. So what I want to say that if you have a regular expression like this one, a plus b star into c, then first you have to execute this clean star, and then you have to execute this concatenation, and then after that you can proceed it with this one. If I have some maybe this one annotation, let's see it will work. So first I have to execute this b star. That's why you can see b star and it is parenthesized. And then I can maybe change the color. And then you have to execute this one and this C. So that's why it is B star into C, and then it is again parenthesized here. And finally, you have to execute this plus. I have to execute this one. Maybe I can use some other color. Finally, I have to execute this one. That's why you can see that the result of this one, union A, and then we have a parenthesis over this whole expression. So with this example, you are seeing that the first precedence is the precedence of this clean star, and then second precedence is the precedence of concatenation, and then the third precedence here in this regular expression is the precedence of this union. So this is the precedence here. Now, so there are some regular expressions here, and now we have to inform that either the left hand side is equal to the right hand side or not. And the alphabet symbols is only 0 and 1, which means the string that I will have here, the strings that I have here uh, will contain 0 or 1 symbols and nothing like that. And nothing, uh, and nothing outside of these symbols. I can only use 0 and 1. I cannot use X and Y or A, B, C or whatever. I can only use 0 and 1. 0 and 1 alphabet should be the part of the strings that I will consider here. So there is a regular expression. I don't know for what language it is, but there is a regular expression here, 1 star into 1 plus null, and this is something on the left hand side, and this is equal to this one, 1 star, which is on the right hand side, and this is equal. For example, you can multiply this 1 star with 1, similarly r star and 1, and what I will get? I will get 1 plus. And then I can 1 star, you have to multiply this with this null, and what you will get? 1 star. So here I have 1 plus, here I have 1 star, and it is again equal to 1 plus and 1 star. What are different strings which are possible in this regular expression 1 plus and 1 star? All possible combinations including null. So that's why 1 star on the right hand side is okay. It's perfect. It is, so left hand side is equal to the right hand side. This is true here. Again, 1 star into 1 star, this is a concatenation and it is equal to 1 star. Yes, it is clear. 1 star means all possible strings of 1, ones including null, concatenated with all possible strings of ones including null. So what I will get? I will get 1 star, all possible strings including null. So that's why this is again true. And now here we have another regular expression, 0 star, 1 star, and then the parenthesis and the whole clean star. So you can prove it by opening these all clean stars, and after applying the concatenation operation, which is very much similar to multiplication, and then finally you will have some set of elements for that language, and then you can also produce some set of elements from the right hand side. And if the set of elements on the left hand side and the right hand side are equal, then you can say that this left hand side is equal to the right hand side. So it's quite easy. So for example, here left hand side, I am taking this left hand side here on these nodes. So 0 star, 1 star, whole star. I can write it in O, in a very much open form like this one. 0 star means null, and then for 1 0, and then 2 zeros, and then 3 zeros. So this is the possible set of strings for this 0 star. For this 0 star, this one. Now I can change the color. Now For one star, I can say it is for first is the null and then single one and then double one and then triple one and so on. This is the opened form of this one star. And I have a parenthesis and then you can write this whole star here. Now what you have to do, first you have to multiply this inside and then afterward you can evaluate finally this one. So just leave it. And now I want to move on. So, so now multiplication of this set and this set on the right hand side. So first, so null multiplied with this null, what I will get? Null. Okay, and then null multiplied with this one, what I will get? One here. Null multiplied with this double one, what I will get? Double one here. And similarly triple one and so on. So after multiplying, so after multiplying with after multiplying this null with this whole set, what I will get? I will get this whole set. And then afterward, what you can do after that, I can do I can multiply this 0 with this whole set. And what I will get? 0 multiplied with this null, what I will get? 0. 0 multiplied with this 1, what I will get? 0, 1. 0 multiplied with this double one, what I will get? 0, double one, and so on. Comma. After that, you have to multiply um, this double zero with this whole set again. With this whole set again. And what you will get? You will get something here. But I have mentioned here and so on. But for example, double zero and then so in this way, all the element sets will go on and go on. A long series of a set of elements you will get here. And then finally you can put parentheses over here and then you can represent some represented with the star as you are seeing here, star here and star here. Now, what is this one? So this is, for example, now you can further simplify it. Now you can reduce because you will see there are many strings which are repeating here. So now you are removing the anomalies here. So for example, you can only mentioning this null here for one time, and if it is coming again in another set, then you don't have to repeat this null again here because this is only one string. This one is here, you and then you can mention this one here as you are seeing here. This 0 is here and then you can put this 0 here as you are seeing. So you have to remove duplication and then you can write all the strings that you have obtained here. And what you will get, what you will get, what you will get would be a set of elements like this one. And this is what I'm getting 0 and then 1, then 0, 1, 1, 0, 0, 0, 1, 1, and then null. So it is again all possible combinations of 0 and 1 including a null. So what is this set giving me a conclusion? This set is giving me a conclusion. All possible strings of 0 and 1 including null. So this is a possible string of 0 and 1 but in concatenation form, 1 0 double 0 and so on. So I can write this whole set as 0 plus 1, 0 union 1, and then whole star. And what this regular expression is giving us are giving us the meaning all possible combination of 0 or 1 including this star, including null. So I can represent this my theoretical statement into this mathematical form 0 plus 1 whole star. So, and this is the same thing which is mentioned here on the right hand side. So that's why the left hand side that we have started working on here is equal to the right hand side. So in this way you can prove the regular expression if regular expressions are given in this format. For example, if some regular expression is given on the left hand side and if some regular expression is given to you on the right hand side, and if it would be asked that you have to prove that either it is equal or not, then this is the way you can prove by taking left hand side, evolving that left hand side, and then reaching on the right hand side. Then in this way you can prove it that some left hand side of a regular expression is equal to the right hand side of some regular expressions. Okay. Okay, now just moving on to uh, clear. So clear all drawings, so all drawings are clear. So now I can start. So now there are now the actual examples of regular languages and their regular expressions. So now in this example, the definition of some language is given in theoretical statement, and then what is my duty? I have to convert that theoretical statement into mathematical definition for the language first, and then I have to convert that, I have to build a regular expression for that language. For example, here, what this theoretical statement is saying said L is a subset of 0 or 1 whole star, which means all possible strings of 0 and 1s, including null. So L is a language which will contain all possible strings of 0 and 1, including null. But we are saying that L is the language over 0 and 1 of all strings of even length, and in this example we are given with a condition that the strings of that language would be of length even. So I can produce all possible strings of 0 and 1, but a condition is given to me that the length of the string would be even and not odd. For example, here, and how I can write it in mathematical form, L is equal to 0, 0, it is even form, 0, 1, comma 0, 1. This comma means union, you can understand, or you can understand plus. When I will convert this language into regular expression, then I will change this comma into plus. This is a simple rule I know. So 0, 0 is the possibility of this language with even length. 0, 1 is also the possible string of this language with even length. 1, 0 is also the possibility of this language with even length, and similarly for 1, 1. So if I can write 0, 0, comma 0, 1, 1, 0 and 1, 1, and then curly braces and a whole star, what I'm saying, I am only giving you uh, the strings with even length, and then I am giving you the clean star, which means all possible strings. And I am giving you only even length here. So I can produce further the strings with even higher length than this two. I can produce strings with length 4 or 6 or 8 or 10 or 12, but all these things are even. So the regular expression is simple, removing these curly brackets, so and replacing it with parentheses and then putting star. So this is 00, or I am writing 00, and then I am changing this comma with the plus. So 00 plus 01 plus 1011. It is very much simple. So this is the simple form, or I can write this as 0 plus 1 into 0 plus 1 and then whole star. This is again equal to this one. So that's why it is mentioned here. And how you can check it? You can check it with multiplication. You can open it up and you can make the possible strings, and the strings that you will get would be equal to this one. And that's why I can say that this regular expression is equal to this one. And the method of opening some regular expression into the form of string, this is something you have seen here, left hand side equal to right hand side. So if you want to check that how it is equal to this one, you can open up its strings, and you can open up its strings also, and then you can compare that the strings are equal or not. Or you can take it as a left hand side and then you can make it equal to this right hand side, or you can take this in a vice versa direction. And the practice we have already did here. So but it is equal, it is a fact, so you can check it by yourself now, because now you know the method how to check it. Now the uh, next example is theoretical statement is strings with odd number of ones. Strings with odd number of ones. So I have a language and my supposition is same over 0 1. Okay, for all my examples. If alphabet set will be changed, I will mention that now the alphabet set is changed. But here alphabet set is not mentioned, so it means that the previous alphabet set is going on here in this example. So but the language is saying that the strings that I will get from this language will be with odd number of ones, which means all possible combination of 0 and 1, but the string that I will get from this all possible combinations must have odd number of ones. Either the number of ones would be 1 or 3 or 5 or 7 or and so on, odd numbers. And very much complicated regular expressions for this language is written here. By the way, as you normally do in programming languages, if I will give you some assignment to build some program, and then there is a possibility that the one student would come with some different logic and another one would come with quite different logic. So as there are different possibilities uh, to solve that problem, same is the concept here for building the regular expression. Many students can come up with different regular expressions, but all the regular expressions are doing the same job. Uh, for example, for this can perform the same job. For example, if I would give you this assignment, that you have to produce regular expression for the language that can produce strings with odd number of ones, then the students can come up with the different solutions or with the come up with different regular expressions. But if those regular expressions are correct, then we can see that the regular expressions are different, but they are producing the same result according to this language. So it is possible. That's why here this one or this one or this one or this one is written here, so that you can get that understanding that different regular expressions are possible. So one regular expression for this language, strings with odd number of ones, is mentioned here. So z odd number of ones, zero can come in the beginning of the string or at the end of the string. So zero is not, you have to mention zero somewhere, but odd number of ones. So for example here 0 star 1 0 star, what this part is giving us, this part is giving us all possible combination of zeros, all possible combination of zeros at the end, but only one, only single one, which means the number of ones here in this part is odd, only one. But multiple zeros can come in front of this one, multiple zeros can come at the multiple zeros can come after this single one, and then it is concatenated with 1 0 star 1 0 star whole star. If I repeat, this star means I can produce a null string that's from this portion, or if I repeat it with one time, then what I will get? I will get one, maybe I can get null here, and then one, maybe I can get null here again. So I can get one here. So one from here and two ones from here. There is no any star over these one, which means that these ones is these ones would be produced compulsory. And if it is compulsory, then I am getting two ones here, and one single one is coming from here. So 2 plus 1 is 3. So again, the number of ones is odd. So I can also discuss this regular expression in further detail, but it is better to do practice by yourself. And how you can practice? You can open it up in sets like this one, like this one, and then you will see that either this expression is giving you some true strings or not. And if this regular expression is not okay, if this regular expression is not correct, then only one string, which is a valid string but not producing from this regular expression, can deny this regular expression, that this regular expression is false for that language. If some valid string is not producing from that regular expression, only one example. This is called what? This is called counter example that we have seen in lecture 1. So this is also the same. This is a different regular expression, but producing the same result as in one. Similarly, this one. Or I can write this regular expression in this way. uh, I will discuss this last one. Okay, and I am leaving these things up to you so that you can practice yourself. This correct version is also the same regular expression producing the same result as these regular expressions are producing. So I will discuss this one in detail, but I am leaving these regular expressions for your practice. But before that, something is mentioned here. And what this thing is saying that we have a regular expression here, 1 0 star 1 0 star whole star 1 0 star, and there is a question here that either this regular expression is similar to all these regular expressions here and here. And the answer is no, this regular expression is different from these ones and this one because some valid string 0. 0 is strings with 0 in the beginning are not producing. For example, what is the problem? Sorry. So now again, This the problem statement was language of strings with odd number of ones. So it means 0, 0 with odd number of ones. This one. So this is a valid string of this language, 001. Here the number of ones is odd. So this is a valid string. So can I produce this string from this regular expression? No, because in this regular expression, 1 is coming earlier than the zeros. And if this is the situation, then I cannot produce this valid string from this regular expression. Let's have a look on the board. I can write the regular expression on the board first. And then I will discuss this with you in a close-up. So now I am stopping share, and now I hope that the video will be larger. So my problem statement was that the languages. My problem statement was what? The languages. The language of strings that can produce strings with odd number of ones. So this 001 is a string and it is containing odd number of ones, and it is a valid string of this language. So now question is, can I produce this string from this regular expression? As we are saying that, because we are saying that this regular expression is we are claiming that this regular expression is correct. If it is correct, then this valid string must be passed from this regular expression. So how can I check that this string can be passed from this regular expression? Okay, so I have a whole star here, which means that I can produce null from here. Null from this part, and then this 1 0, which would be 1 0. Okay, and here odd number of ones. So this is something, okay, I can produce 1 0 is a valid string. Okay, no issue. Now, how can I produce this 001? Can I produce 0 from this part? We can say I can produce 0 and this 0 from here. Oh, how? But it is not possible, because then this one will come as a compulsory part of this string that you will get from here. If you are getting 0 from here, then this one will come automatically along this one. Okay, for example, I can produce null. And then if you repeat this whole portion for one time, then this one will come, and I can produce null from here, but I have to produce the zeros. So I am repeating it, this star for one time without null. So I am getting 0 from here. I can get 0 from here. Similarly, then this one is without any condition. So this would come again. And then this 0 star, I can take 0 from here by executing it one time without null. Even I can get null from here. I know that. I can get one null, one null, which would be equal to 1 1. I can also get 1 1 from here, but this is not the example here. I have to I have to produce zeros, two zeros, and I can produce, when I will produce two zeros like this as I am producing here, then one will come compulsory, and then I am not getting 0 0 in combination like this one. My string here that I am getting is not 0 0, but it is 1 0 1 0 from this part, and this 1 0 is without any condition. So this 1 0 will again become the part of that string, and what I will get from this whole regular expression, if I am attempting to produce this string, I will get this string, and these strings are always starting with 1 due to this one. And if I am getting null from here, then I will get this 1 0 only, and this is again starting with 1. So this regular expression is not able to produce strings starting with 0. So that's why this regular expression is false, because this is only one example which I want to produce from this regular expression, but this expression is not giving me this permission to produce this string from here. Hence, this regular expression is false. Okay, let's move on. Uh, Now I can share the screen again. So now here. So that's why strings with 0 in the beginning are not producing from this regular expression. So that's why this regular expression is false. So this is also the correct version of the for this language, like other regular expressions here. And I said that I will discuss this one here in detail. So now I am discussing something. So let's have a look. First, I am writing this regular expression here from the slides, and then I will produce some strings from this regular expression using hit and trial method, and then I can claim finally that now this is okay. Okay, I am now stopping the shared screen again for a close-up. So now this is the regular expression from the slides, and now I have to prove that this is the correct regular expression for the language of strings containing odd number of ones. So okay, what I can get from here, I can produce null from here. So okay, make it null. And then what I can get from here at least, so this is the whole star like this one. So what I can do, I can get null from here. and then 10. Okay, 10. So what I will get? I will get 10, which is a valid string. Okay. Again, uh, so this 0 star is now making this regular expression to produce strings starting with 0, and it is null here. So if I want to start some string with 1, so then I can make this part null, and then I can start from this 1. I can start, I can generate string from this part, and then this part will give me string starting with 1. So this regular expression is making me enable or making me able to produce strings either starting with 0 or 1. Either starting with 0 or 1. So this condition is making me able to start or to generate strings starting with 0, and this star is making me able to make it null and produce some string which can start with this 1 and this one, and then 0 star, all possible combination of zeros. So and then this one, so this one and 1. If I will execute this part for one time without null, so what I will generate, I can generate this 1 here. I can I can make it null, or I can produce some 0 here. So I am producing null for the first time. And then 1, and I am producing null here. And now this part is ended, and now this is the compulsory part. So 1 0, and what this string is saying. So now null 1 1, 1 null 1, this one. So this is the string. This is also a string that I can generate from here, and it is starting with 1. Now, so what I am checking different strings using hit and trial method just to convince my mind that this regular expression is correct. So you have to do the same practice. After building some regular expression, then you have to execute some strings over it. Uh, and and when you will tie it up, then you can say, and if all the strings are generating from your invented regular expression, then finally you can say this regular expression is correct. uh, but it is uh, not something, a final statement that you can say that it is correct. Maybe if your regular expression is quite complicated, then maybe some other person can come up with some idea or can come up with some string that your regular expression is not producing. Then only one that legal example is enough to negate your regular expression. Keep this thing in your mind. And when I will give you the assignments, or when I will give you the uh, exam, then you have to produce the regular expression like this one, and then I have to check, I have to verify different strings over your regular expressions uh, for verification of your regular expression that either those regular expressions are correct or not. So being a teacher, I can check 4 or 5 different strings, and if all those strings are okay, then I can say it's okay. I will give you the full credit of that question. Even if your regular expression is false. But if it is not coming into my mind, then you can take the benefit of doubt. So anyhow, leave it. Uh, Now I can produce 3 zeros from here. I can produce, if I can produce 1 from here, five zeros from here, then this one, and maybe two zeros from here, and this is now this part is ended, and then finally 1 0. So this is again a valid legal string of this regular expression. And for example, now without checking this regular expression, now I am checking. So what is this language? This is a language of strings containing odd number of ones. So I can write, okay, any string in my mind, any string. So for example, 1 0 0 0 1 1 0 0. So this is any string. Whatever comes in my mind, I just write it over here. Now I am going to check that this string, which is a valid string, odd ones, three ones, odd number of ones. So this is a valid string. So now I'm going to check that this string is passing in this regular expression or not. So okay, this one I will get from here. I will get this one from here. Okay. These three zeros I will get from this part. All these three zeros I will get from this part. This one I will get from here. Ah, maybe odd number of ones. Hmm. Let's see. First making it null, then one, three zeros, then this one, then null, and this one from here, 1 0 from here. But this zero, last one, is not coming from this regular expression. Hmm. Let's see, otherwise, so this string is giving me a result that this regular expression is false. But let's have a check over it once again. Maybe we are not up to the mark. Hmm. So let's see, 1 0 0 0, 1 0 0 0, and so on. So now, so we have seen that may be some error in it. So because this is a valid string and it is not going to be passed into this regular expression. So what is the issue? So one is from here, 0 0 0 from this part. This one is from this part, but again one. So what I can do, I can move on to this one because now this part is ended. So this one is from here, but this 0 0 0, and I am getting only the zero from here, and this next zero is not coming. Maybe zero star here, maybe. I don't know, but if there is a zero star here, then I can produce this one. So let's check over the nodes. Let's check over the nodes. Uh, so now see, let's see the next example. Strings of length 6 are less. So the regular expression is length 6 are less for all possible combination of 0 and 1. Keep this thing in your mind that the alphabet set is 0 and 1. So all strings of length 6 maximum or less, which means that the uh, length can be 6, 5, 4, 3, 2, 1, and even null. So, so 0, what I can generate 0 or 1, 0 or 1, 2 times, 0 or 1, 3 times, 0 or 1, 4 times, 0 or 1, 5 times, 0 and 1, 6 times. So from these different parts, I can either produce 0 or 1, 0 or 1, and I am writing this 6 times. So finally what I will get? 0 plus 1 raised power 6. So I will get the strings from this regular expression, which will have surely the maximum length 6 or less. And if I want to make null as a part of this expression, then I can write 0 plus 1 plus null raised power 6. And this null is just to allow null in the regular expression. And this one was a simple case, and you can now check it by yourself. The next example, strings ending in 1 and not containing 00, which means all possible strings which will end up in 1 finally, but those strings will contain this substring 00. So 00 must be the part of string, and the string would end up at 1. Okay, so strings ending in 1, so I can write either 1 plus 01. What it means? 1 can be produced or 01 can be produced. This part is again containing 1 at the end. So if you write 0 here, then the regular expression would be false because you are producing only 0, which can be the uh, which can come at the end of a string. So that's why now in this regular expression I am not writing 0 plus 1 or like that. So I am writing 1 plus 01 whole star, all possible combinations, and then again only one time 1 plus 01. This part is the confirmation that all possible combination, then the string will end at 1 or 01. And then the strings will not contain 00. So that's why it is 01, just to not permit the substring 00 in the string. Sorry, in the first I said that I have to allow 00 in the string. No, it is not. The condition is not containing 00. So that's why it is 01. And I can also from my previous knowledge I know that r star into r is equal to r plus. So by using the same rule I can say that this is equivalent to 1 plus 01, and not clean star, rather it is plus. It is union. It is plus. Here plus means all possible combination without null. Because if I can produce null as a string from this regular expression, then null is not a string which is ending at 1. And it is not so ending in 1. So then it is a illegal string. So that's why I am writing plus here, just to remove the null string from this one. You can check it by yourself, or just in a very maybe maybe on the next examples I can explain, but this because this is the simple one and you can practice by yourself. Now 5, language for C identifiers. C identifiers, programming language C. And in C programming language, how you can declare a variable. For example, if you are declaring int and then writing some variable name, that is called identifier. And in C, we are allowed to use uh, small alphabets and the capital alphabets and the digits from 0 to 9. So these things are allowed, and also the underscore is also allowed. So what I am writing here, so is a L is something which is containing small lowercase letters from A to Z, and comma capital letters A comma B comma and so on, capital Z. And D is what? 0 comma 1 comma 2 and so on, 9. So 0 to 9 digits. Now I am writing the regular expression, which is quite easy one. Regular expression is equal to L, which is this one, plus underscore. What I am allowing here in the beginning, so I can use lowercase letters or the capital letters or the underscore in the beginning of the variable name. Okay, and into the concatenation is L plus D plus uh, L plus D plus underscore. And now I can also use digits after introducing the first letter here. So here I can use annotation. So here in this part, I am introducing the first letter of the variable name, which can be lower letters or capital letters or the underscore. Digits are not allowed uh, in the beginning of a variable name. However, after writing the first letter, now here in this part, we are allowing digits here, that after writing the first letter, we can use the digits here. So L plus D plus N and whole star, which means any combination of lower case letters, uppercase letters, and underscore. This was an easy one, so leave it here. Hmm. I want to clear all these drawings and moving on. So now the next example is strings ending with zero. Strings ending with zero. So the language with strings ending with zero. So the last symbol of the string, the last alphabet of the string would be zero. E.g. So what you can see, 0 plus 1 whole star, it means all possible combination of 0 and 1. And then yeah, you can just put 0 at the end in concatenation. Now this is the proper correct regular expression for all combinations of zeros and ones ending with 0. And this was the definition of this language. So here in this thing, because the condition is only strings ending with 0, and before that, which means any combination, so it is simple. So when it is simple, you can write 0 plus 1 whole star, which means all possible combination, and then end it with 0. So this one an easy one. Now moving on, just clear the drawings. Clear the annotation. Now this 7 and 8, in this example, I am asking to write the algorithm for some language. Algorithm means give me the logic, how you will produce a regular expression. I am not asking for the regular expression, but the idea which is coming into your mind for solving that language into regular expressions, that idea I am actually demanding when I am writing algorithm for strings. Algorithm for strings with next to last symbol 0. What I am saying here, that here if next to last symbol is 0, So if this is the string, and if this is a string, then next to last, this is the last symbol, and here next to last symbol would be 0. So here I mean that all strings in which next to last, this is next and this is the last, next to last would be 0. So if I have to, so if I have to uh, produce a regular expression for such a language, then what I have to keep in my mind first before generating or before writing that regular expression? So now, if next to last symbol is 0, then it means that 0 is the compulsory part. Then it means that null is not a proper string for this language, and also only single one is not the proper string for this language, or even at the end, even at the end, uh, just look over these slides. Uh, Even at the end, this one is also not the proper example, because this one should be this one must be 0 according to this definition of the language. So this is one statement that I don't have to allow in my regular expression. And then similarly, the string is 0 if string is only 0 or ends with 10. This is also something illegal. Strings only 0 means it is ending with 0, but next to last symbol must be 0. So that's why 0 is also not a proper string of this language. And similarly here 10, it means that the next to last is 1. So again, this string is also illegal string. So I don't have to allow this A and B for this language. So this is the idea, that you have to think first before generating the regular expression for this language. So, and then these ideas that you have to write, if I am asking that write an algorithm for this language. So that's why these are the steps that are coming into my mind, and I'm writing those steps here, and this accomplishes my algorithm. See, and now what are the proper languages? If the string is like this one, 0 0, then it means next to last is 0. This next to last, this one is the last one, and this is the next one before the last. So this is 0. So this is according to the definition of the language. So this is something legal. The strings end with 0 1. So next to last is again 0. So this is again a legal string. So I have to allow, so I have to allow these C and D, but I don't have to allow these A and B. So this is something, the logical steps that I have to write, and this concludes the algorithm for this example. Now, mm, algorithm for 4. And my example 4 is what? Strings ending in 1 and not containing 0 0 1. So I am asking, in this example, I am asking algorithm for 4, which is ending in 1 and not containing 0 0. So this is an for your work. You have to work over it by yourself. You have to think the steps like this one, A B C D, by yourself, and you have to write the steps for this example by yourself. Now moving towards some other concepts. This is the end. Now you have the definition of regular expression, and now you have the understanding that how you can generate or how you can write the regular expression for some regular language. So you have now enough practice in this lecture, but you have to do this practice by yourself, and you have to spend sufficient time, too much time I can say, to practice. If your practice would be much or higher, then you will be an expert of writing a regular expression for any kind of for any regular language, that I will give it to you and you will write the regular expression speedily. And it is only possible when you will spend sufficient time in practicing these things. Now, the next concept is drawing some flow diagrams. For example, if the example is strings ending in zero, how you can write the flow diagram for it? You have to start with the arrow, then you can you can draw some circle which is representing some state, or you can say initial state ending in zero. Then you have to take zero, and after taking zero, only zero is the part of this definition. So after taking zero, this string can only zero can be a string. So just taking input zero, and then you can come up on a, final state or a for acceptance states. So this is the initial state which is represented with this arrow, and this double circle state is representing a final state, and these arrows are representing the inputs. Uh, Here, if there is only zero, then you can take that zero and you can come up on this final or acceptance state, which means that the string, okay, I can explain it on this small board. Just a minute. हाँ
ये ठीक है।
हाँ ये ठीक है बेटा, जानिए।
ये रात है तो इसके साथ लेगी पहन लूं।
हाँ ठीक है।
सुबह कुछ सही वाला पहन लेना।
हाँ ठीक है ठीक है।
सुबह वैसे नींद
चलिए नीनी ना 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 करो आप, फिर मुझे अब थोड़ा सा पढ़ाने दो, वरना ये बच्चे मुझे मारेंगे जो इधर पढ़ते हैं। Sorry. uh, my daughter was in the lecture and he was asking something, maybe you have heard, and I have to reply her actually. So sorry for the delay. Uh, this is online teaching and at a physical distance, and and if you are giving or if you are lecturing from the home, then these things can happen and you have to bear these all things. So anyhow, just move on. uh, So basically now these flow diagram is giving you the concept about the next topic which is coming up in the next lecture, which is about finite automata and how you can draw finite automata. So this flow diagram is giving you that concept. So ending in zero, strings ending in zero. So if there are strings ending in zero, then it means 110 is a valid string. 010 is a valid string, or you can say 000 is also a valid string, or like that. And if you have to draw a flow diagram for them, then you have to first use an arrow first. This is which means that this is something initial state, and you have to represent state with circle. So this is the initial state now. So if this is the string, or what is, you have to first think the minimum strings. So the definition of the language is ending in zero, strings ending in zero. What would be the minimum strings? What would be the minimum strings? Zero. Only zero is a valid string because it is ending with zero. And what is the, so then you have to think the, okay, starting state, and then you have to give zero. So this is the minimum string. You have to accept, or you have to pass that minimum string towards the final state. And if it is a final state, then you can represent it with double circle and uh, you can represent it with double circle and okay. And then what it is representing in the initial state, you are taking this zero and then you are giving you are reaching at the final state. So now your this minimum state is accepting here by this flow diagram or by this finite automata. But in finite automata, if the alphabet set is 0 and 1, then every state must have these two inputs or outputs, 0 and 1. So here, this state is uh, only showing one output, which is 0. And you have to think about its another output, which is 1. So where you have to put that one? I can put this one also here, but if I will put here one, then what it means, if I will put it here one, then it means that either taking zero or one, you are reaching at the final state. But according to the definition of this language, ending with zero, but here you are allowing that if the minimum string is one, that then this finite automata will accept this string which is wrong actually. So I cannot put this one here, only zero is okay. So what is the other option then? Other option is then I can make a loop here and then I can represent it with one. So now the two outputs of this states are now finished. And now, okay, here okay, if this state is accepting one, then this is some common idea, but it is not true. Then I can represent this arrow and then I can label it with one because this one is going here. So this is a general idea that I can use some arrow here. But it is not always true. Keep this thing in your mind. And then, okay, this state has only one output, outer degree, and you have to complete its outer degree because there are two symbols in it and the okay then this would you can represent it with 0. And now you can check these legal strings 1 1 0. So 1 again 1 and then 0, this would be passed. 0 1 0, okay, 0 1 and then 0, okay, this would be passed. 0 0 0, so 0 and then one second 0 third 0, this will be passed. Maybe it is okay, I think. So now I will move towards the notes now. uh, Now look over these notes and here you are seeing that okay 1 is 0, so this is okay according to our board representation. Now this example is saying next to last 0. Next to last means last symbol or last alphabet of the string could be any, but before that one the second last should be 0, second last. So I can start with some, you can also put a b c r x y z in these states like this one a b c d. So I can start with this state by putting some arrow making some state and the next to last 0, so the second last symbol should be 0. So 0 1 would be a valid string of this string. So that's why by taking 0 and then by taking 1 I can reach on some acceptance state, that is okay. But and 0 0 1 is also a valid string, so now you have to think 0 0 and then taking 1 and reaching acceptance state. This is also now accepting in this finite automata flow diagram. So 0 on this direction and 1 is here, okay. uh, two output two output degree of this state is also okay, 0 and 1. This is something okay, 0 and then, so maybe I have to, this is an easy one, so you can do by yourself. Maybe I have to focus on the next examples which are coming here on this one. uh, Anyhow, let's have a check. Don't blame me in future that I didn't These are actually now you have to, so next to last 0. So it means the minimum string is 0, next to last is 0. 0 0 is also valid. 0 1 is also valid. Or 1 0 is not valid because next to last is not 0. So 1 0 is not allowed. 1 0 should not be allowed. Uh, and then 1 1 next to last is not 0. So this should not be allowed. So now you have to think over on the screen. You have a finite automata. First think over 0 0. So start with this A by taking 0 and then 0. So this is a valid string according to this one. This is a valid string. Look at this board. This is a valid string and these boxed strings are not valid strings. So this is 0 and then 0 and you can make it a final state or you can represent it with double circle because this is an acceptance state. So 0 0 now it is accepted. So one edge is complete, the other one may be a loop. So you can just put a loop here and represent it with 1 because or it can go towards some other state. This is also possible. This is not something always a rule that you can put a loop here, but probably there is a loop here. Okay. It is always better to take some strings and then also draw your finite automata in parallel. Then you will reach somewhere with a value or with a true direction. So okay, 0 0 up to this part, up to this point only this part is okay. Okay, with 0 0. Now you can think over this string which is 0, which is 0 1, which is also a valid string 0 1. So okay, start from here. Okay, 0 and then moving on here. So this is the direction of 0 1 and you are reaching at another state. You can draw another state and uh, this is a legal string which is accepting. Now 1 0 1 0 which is a illegal string, and if it is illegal then it should not be passed from this finite automata. uh, 1 0, okay. So if I make a loop here 1 and if I make, and after that I can take okay 1 and then I can take 0 and it is in between this finite automata and I am not reaching at this at these final states. So it means that this is an illegal string and this is not reaching at the final states, so that's okay. So this design by making a loop here with 1, so this is also okay. Now maybe I can use some other color with dark color. Maybe this is something illegal. And now the two output degree of this state is complete. The two output degree of this state is also complete. This state output degree of this state, output degree of this state is incomplete. So now you have to think. So if if there is a string 1 1, then okay 1 and then 1 you are here at this state and you are not reaching at this one, so this is again perfect. And finally, if your string is if if your string is 0, sorry for the board marker, sorry, if your string is 0 0 1, if your string is 0 0 1, then this is 0, this is 0 and now this is 1. So this 0 0 1, the next to last is 0 and this is This is a legal string area, and I am reaching at the final state. So now I have to draw this one. You have to label it with 1. If 1 is going here, then probably 0 is going here. So you can make a loop here with 0. And now, if your string is if your string is 0, okay. If your string is 0, 1 and 0, 1. So next to last is 0, and this is the legal string 0, 1, 0, 1. Now think this string over this FA. Okay, this is 0, this is 1, and then again 0, 1. So you have to put arrow here 0, and then okay, you can reach again here 0, 1. So in this way you can put a loop here. You can put not a loop, just you can put an arrow with the 0 here towards B and then 1. So the other degree 0, 1, 1, the other edge can go toward these all states, but maybe with one string 0, 1, and then 1, 0, 1. So then you have to put this one here. But this is a method of hit and trial that you have to do for the valid strings, and then you can conclude that I have to put arrow in this way or in this way. You have to practice these things. Okay. Uh, I have to do something speedily because the battery is finishing. So now this is a finite automata uh, for language ending with 1 1. Look, regular languages have regular expression. And what is the machine that can evaluate a regular language? That machine is called finite automata. And what you are seeing here is basically the finite automata. So what I can say we can build a finite automata for all regular languages, because finite automata is a machine for validating the regular languages. So now languages ending with 1 1. So this is quite easy. So you have to start ending with 1 1. So 1 and then again 1. So you have to first think in this way. Ending with 1 1. So start with 1 and then again 1, and then you can reach at this one. So you have to build this one first, and then you have to think for the other possibilities, and then you have to draw. For example, it could be 0 0 1 1. So 0 0 1 1. So it means that loop of 0 should be here. And it could be ending with 1 1. So it could be 1 0 1 1. So okay, 1 0 1 1. So 1, so maybe 0 in the previous direction, and then 1 1. So this string is giving me an idea that I have to put the arrow in the reverse direction. And if the string would be triple one, triple zero, triple one, which is a valid one, so triple one like this one, so I have to put one here. Triple one, triple zero, 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 and then again triple one, 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 and again one. So this string is giving me further clues to finalize my finite automata. So in this way you have to think. And anyhow, now moving on to next example. I am just now speeding up the things. I will maybe discuss this one in detail. Yes, I think this one because it is a different. But first, uh, just give me some time. Mm, and I am just coming back because my battery is finishing, so I have to take the charger. Just wait. So I am now back with the charger. So, and it is better for me to take another board marker. So again, wait. Rather than waiting, maybe I have an option of uh, stopping the yes, pause. Okay, now I have a new board marker of my little daughter who was asking something to me a few moments ago that you have heard. Okay, and yeah. So now the regular expression is sorry. Um, Now the language is even number of zeros and odd number of ones. Even number of zeros and odd number of ones. Maybe we have uh, even number of zeros and zero, one. Uh, so number of zeros can be even, like this one, and number of ones can be odd. So this is the minimum example. Number of zeros can be even, number of one can be odd. So this is the minimum example, and null is not the proper null is not the proper null in an illegal string for this language. Okay, zero is illegal string. Only one is illegal string for this language, and maybe zero one is illegal. 1 0 is illegal. 0 0 is also illegal because number of zeros is even, but there is no one here. And similarly, 1 1 is also illegal. So the minimum string is this one. So now look over here on the notes and you can see this is the starting state. So what I can say, okay, I can draw something like that. Okay, by taking 0, I am moving towards another string. Minimum string is 0 0 1. So 0 and then 0 and then again maybe You can also 0 and then 0. I am drawing the this FA according to the notes, so that's why it can be a little bit different. But I am drawing according to the notes so that you can understand. So if I draw in this way 0 and then maybe 0 and then maybe 1. Okay, so this would be the 1, this would be the 001 minimum string. This would be one possibility. And and this is the final state because 00001 is something like that. Okay, this is the minimum string. Now make it a little bit further. For example, even number of zeros and odd number of ones. So 100, like this one. So if it is like this one, 100, which is a valid string. So 0 is on this way, and I cannot put 1 here because then it is something always produce errors. But sometime it is necessary for NFAR like that. So if I produce 1 here, then I am allowing only one string 1 to be accepted. So this is not a valid thing in this diagram. This is not a valid thing. So now this is giving me a clue that I have to change my design, because if I put 1 here, then I am actually making some way for this string 1 to be accepted, which is not good. So I have to shift a change, maybe 0 0 and then uh, 1 here. 0, maybe if I will put 0 here, then my previous string 0 0 1, then my previous string 0 0 and then 1 here, this one 0 0 1 here is accepted, and now this one, think over it, 1 0 0. So 1 and then one thing is sure that I can go here 1 and then 0 and 1 0 and then 0 again here, 1 0 and 0. Now this string is also accepted and this string is also accepted. So now this is a new design. Okay, now take these examples here, that these two strings are now passed, which are the legal string, and now take another, write these passed strings here, and now take another string just to complete your diagram, because now okay, one output degree, one, so two output degree of this state is finished, but this state still have one less outer degree. This state has also one less outer degree, and also this state has also one less outer degree. So I have to work over this diagram further. So what is my language? Number of zeros can be even, number of ones can be odd, and so 0 0 1 1. Number of zeros is even, number of ones can be odd. So okay, this is now my new string. So 0 0 1, and okay, for up to this part is okay, but what is for this one, because number of odd is 1, number of even is 0. So 0 0 1 and 1. So what I can do maybe, so okay, 0 0 1. I can move one here and then one here. Yes. So 0 0. I am just making a room for me. So 0 0 1. That was previous one. So 0 0 1, and then again 1. String is 0 0 triple 1. String is 0 0 triple 1. 0 0 1 1, again 1. So I am again on the final state. This is accepted. So now it is 0 0 triple 1 is accepted. I can write this here. And now I have a new edge here. I have designed a new edge. The outer degree of this state is now finite 1 and 1. This is remaining and this is remaining. So 1 1 0 0 0 0. So I am also getting a clue that maybe I have to put 1 here and also 1 here because there is some pattern here. 0 0 1 1 0 0. So from this one I am thus making this shortcut. And this is, if you look over this these notes, then you have this one, and then you can check your other strings over this diagram, that either this diagram is okay or not. If it is okay, then perfect, and now this is okay according to our notes. I can discuss also further strings over this finite automata, but as you have enough understanding for this example, so that's why I just make myself stop here, and so that you can continue uh, making these further edges by yourself. And the last example is ending in 1, not containing 0 0. So this is something that we have seen, ending in 1. Strings ending in 1, the last symbol is 1. So it means that I have to start and I have to put 1, take 1, and I have to reach at the final stage. So this is ending in 1. And not containing 0 0. It means that if 0 0 is the part of the string, then that string would not reach at the final state. So okay, 0 0 would not be the part of the string. So if I am getting 0 and then again 0, then I will not put edge here. I will put edge here, and then can make is some state here, and then I can represent it with, because now 0 and 0, it means that 0 0 is now the part of the string, and this string should not be accepted by your finite automata. So that's why I have introduced a state here, and I have make a loop here with 0 and 1, which means all possible combination of zeros and 1. So whatever the different possible strings that I am getting here over this loop on the nodes, I know that from this path 0 0 is the part of that string. So this string should not be accepted. So that's why this is some state that I have introduced in my finite automata, which will make this string not reach on the final state, which is quite good because this is an illegal string. So this 0, only 0 1, and then 1 I can reach on this final state, because 0 1 is a valid string. And okay, 0 1 0 1, and even triple 1 or 4 1, and then I can get 0 and 1. So this is basically machine. You can check your strings over this machine by yourself, and this discussion is has now given you an idea that how you can draw finite automata. We can normally this we can represent this finite automata with fa. We will practice these things in upcoming lectures. uh, FA is also called DFA, deterministic finite automata. But normally uh, we say DFA as simply FA. If something, if in your literature you will find FA, then it is always means DFA. And what is DFA? DFA is a thing in which the outer degree of every state is equal to the number of the alphabets available in the alphabet set. Okay, at this point, I want to end my this lecture, and I will continue this design of FA in my upcoming lecture, inshallah. So, up to that point, just if you don't understand anything, then we have a WhatsApp group and we have a Zoom conversation also. So, you can also uh, question me there, and I will be there for this thing as I already informed you. So, okay, bye bye.